Okay, now we'll take a look at this example. Now, this series doesn't fit any of the forms of the series that we've looked at. We've looked at geometric series, and this doesn't look to be a geometric series. We looked at telescoping series. This doesn't look like it takes the form of a telescoping series. And we looked at P series. And this doesn't look like a P series, and nor does it look like anything that I want to try to integrate. So the integral test, I probably would not use here. And if I try the nth term test for divergence, when you take the limit of a in this case, you get 0, so the nth term test would also fail. So none of the methods that I've learned so far would help me to determine whether this limit converges or diverges. So what we're going to do here is we're going to do something called direct comparison. Okay, so taking a look at the right here, we have theorem 9.12 in Larson and Edwards Calculus Ninth Edition. It's called the direct comparison test. And it says, let 0 be less than an be less than or equal to bn for all n. And if the series bn converges, then the series an will also converge. Why is that? Well, if you notice, bn, the terms of bn are always above or equal to the terms of an. So if bn is going to converge, it's actually going to squeeze an under it and force an to also converge. So if bn converges, it forces an to also converge because bn is above an. And alternatively, if an diverges, if the one underneath diverges, it's going to force the one above to also diverge. So that's the direct comparison test. All right, so looking back at our example here, looking back at our example, I want to find a series that I can compare this one to that I know the behavior of, whether it converges or diverges. Looking at this, I view this as being very similar to this series, the sum from n equals 1 to infinity of 1 half to the n, which can also be written as a sum from n equals 1 to infinity of 1 over 2 to the n power. This is a geometric series, and because of the fact that the ratio is 1 half, this geometric series will actually converge. So looking at the terms here, if I can prove that the terms of this sequence are greater than the terms of this sequence, or sorry, yeah, if I can prove that the terms of this series are greater than the terms of this series, because I know that this one converges, I'll know that this one also converges. Another choice would have been the harmonic series, 1 over n, and we know that 1 over n diverges. And in order to prove anything here, I'd have to also be able to compare this to the harmonic series by saying that the harmonic series would always be smaller than this. And I'm not sure if that's true. So I'm going to go this route. I'm going to prove that term-wise, this series is always going to be smaller than this series. I know that 2 to the n is equal to 2 to the n. That's a given. Something is always equal to itself. If I add 2 to one side, for instance, if I add 2 over here, or sorry, not 2, if I add n over here, n plus 2 to the n, because I'm only looking for values of n that are um, non-negative integers, this inequality symbol actually changes. This is no longer equal. Now that I'm adding something to the left side is now greater than the right side. And actually, it could also be equal if n is equal to 0. So this is either greater than or equal to now. And if I flip both sides over and I find a reciprocal, it would say that 1 over n plus 2 to the n is equal to 1, or sorry, it has some relationship to 1 over 2 to the n. Well, what relationship is that? Well, since I'm flipping both sides over, if you find the reciprocal of two numbers, the relationship that they have as far as greater than or less than is going to change. So when I flip both sides over, this becomes less than or equal to. So I've proven here that each term-wise, the terms of this series are smaller than or equal to the terms of this series. So that means I have this case over here, the case where I know this one converges, I know that Bn converges, and it's going to force An to also converge. So here's how I'm going to label these two series. This one is going to be my Bn, this one is going to be my An, and what I've proven here is that An is less than or equal to Bn. An is less than or equal to Bn. And I know that Bn converges. I know that Bn converges. I know that this series, which is the geometric series with ratio 1/2, this is what I'm calling Bn. I know that that converges, and because that converges and is greater than or equal to this one, An, I can also say that this series also converges. So, oops, that would be my conclusion. By the direct comparison test, I've proven everything I need to prove. I've proven that An is always less than or equal to Bn, and I also know that Bn converges by being a geometric series. So that means that our series, the sum from n equal 1 to infinity of 1 over n plus 2 to the n power, converges by direct comparison to this one, 1 over 2 to the n, the sum. Okay, so there we have it. That would be the conclusion, that this series converges, and it converges by direct comparison to the geometric series. All right, so let's take a look at another example. Actually, let's see what happens with this example here. Let's take a look at the sum from n equals 1 to infinity of 1 over 2 plus the square root of n. Let's try this one. All right, now let's try to find a series that this one compares to. All right, well, I know that this compares. I could use this p series, 1 over n to the 1/2, or 1 over the square root of n. I could use this p series, n equals 1 to infinity. Let's see what the relationship is of our series to that p series nth term. So, if you start off with the square root of n, the square root of n, and you add 2 to that, then this side is definitely, oops, the left side is definitely uh, going to be greater than or equal to the right side for values of n that are, let's see, if n is 1, then this becomes 1 plus 2, 3 is greater than or equal to 1. So for all values greater than or equal to 1, this is true. Okay, so let's go ahead and do the same thing we did last time. We're going to flip both sides over. So I'll get 1 over 2 plus the square root of n is going to be less than or equal to 1 over the square root of n. So the relationship here is this side is smaller than this side. Here's an, here's bn. Remember, bn is the one that is larger from the direct comparison test here. Bn is the one that is going to be larger for all values of n. And I know that bn diverges. But there's nothing in the direct comparison test that tells me what happened when the larger series diverges. I have information for when the larger series Bn converges. It forces the smaller series to also converge. But I have no information about when Bn diverges. In order for me to use this direct comparison, An would have to be the series that diverges, which would actually be the smaller series, the one that is smaller. So I need to find something else to use for my comparison. So rather than using 1 over the square root of n, let me try to compare it to 1 over n. So I'm going to try to use the harmonic series for comparison. 1 over n from n equals 1 to infinity. I know that this series diverges, and let's see how it compares to our series. Well, let's see. N and its relationship to the square root of n plus 2. Well, if n is equal to 1, then this is 1 on this side, and this is 1 plus 2 on this side, so the right-hand side would be greater. If this is equal to 2, then the left-hand side is 2, and the right-hand side is the square root of 2 plus 2, which is still greater. The right-hand side is still greater. If this is 3, then this is 3 plus the square root of 3 plus 2, and the square root of 3 is 1 point something. So if you add that to 2, you're going to get 3 point something. So the right-hand side is still greater. But when you get to 4, the left-hand side is 4, and the right-hand side is the square root of 4 plus 2, which is also 4. So when you get to 4, they're equal to each other. When you get to 4, they're equal to each other. And when you get to 5, this is 5 plus the square root of 5 plus 2, which makes actually the left-hand side larger. And if it's 9, for instance, this is 9 plus the square root of 9 is 3 plus 2. The left-hand side will be 9. The right-hand side will be 5. So for all n greater than or equal to 4, for all n greater than or equal to 4, the left-hand side is actually greater than or equal to the right-hand side. But that's only for n greater than or equal to 4. So we're only going to be concerned with those, the n's that are greater than or equal to 4. All right, so once you determine that, if you flip this side over, you get 1 over n is less than or equal to, and this is going to be 1 over the square root of n plus 2. And we see here that uh, this would be my an, this would be my bn, the larger one is bn, and I know that an, which is the harmonic series, diverges. I know that the harmonic series diverges. So since an diverges, by the direct comparison test, it says if an, the smaller series, diverges, then the larger series bn also diverges. And I know that beyond 4, this thing is always greater than this thing. Therefore, as n gets really, really, really large, because this one diverges, it also forces this one to diverge. So my final conclusion here is that the sum from n equals 1 to infinity of 1 over 2 plus the square root of n diverges by direct comparison to this one, the sum from n equals 1 to infinity of 1 over n, the harmonic series. So this would be the final result. I find out that this series diverges by direct comparison.